So welcome back. We are now going to get into section 3.2. Remember, chapter 3 is linear and quadratic functions. Okay. 3.2, building linear models given some data. So if you're given some information, can you figure out a linear model that matches that data? So we need to be able to draw and interpret scatter plots. If I have a chart, can I turn it into a scatter plot? If I'm looking at a scatter plot, what data does that represent? Can we distinguish between linear and nonlinear relations? I mean, if I'm staring at a scatter plot, is a linear model really the best choice compared to other things that we'll learn later? And can we find a graphing utility to find what's called the line of best fit? So we'll get into this towards the end of this section. Okay, so if I have a scatter plot and I can find a linear model that matches it pretty well, that's a very useful skill to develop. Okay, and the first step in doing this is just, can I produce a scatter plot? If I have a bunch of data, can I throw them down as points on a graph? So example, okay, the on-base percentage for a team represents the percent of time that a player gets on base out of all of the at-bats. Okay. The data given represents number of runs scored, so runs will be Y, and on-base percentage will be X. Maybe some teams get on base a lot but don't score. Maybe other teams don't get on base that often but still manage to score a lot of runs. So we'll have on-base percentage as X and runs scored as Y. Now, before we get into this, what would a linear relationship represent? Suppose that Y as a function of X, runs as a function of on-base percentage is linear. Well, then what that means is, if I can increase my on-base percentage, I should expect the same, a sort of corresponding, increase in runs scored. And that same increase would happen whether I'm increasing my on-base percentage from, say, 10% to 20% versus 30% to 40%. If I make the same change in X, I should expect the same change in Y. That's a linear model. So here's a big old chart of data of on-base percentages and runs scored, and we're just making a scatter plot. Whoops, sorry. We're going to make a scatter plot using on-base percentage as X and runs scored as Y. So if I have 32.9% on base and 812 runs scored, I make this point, 32.9, 812. And now we've got a whole bunch of data for a whole bunch of teams. Okay. So can we draw a scatter plot and sort of describe what's happening based on looking at it? So the three things we want to do: draw a scatter plot, either by hand or with a graphing utility, and just sort of describe what's happening to the runs scored as the on-base percentage increases. I'm just going to go back to the previous slide to pause there so that if you're doing this, which hopefully we are, you can copy down the data. So here's the chart of data. So can you plot all of these points and describe what's going on? Okay, so hopefully we tried making a scatter plot. So taking all of those points and plotting them, you should get something that looks kind of like this. Now, this isn't a straight line. I certainly can't draw one line that represents all this data, but it's kind of close, okay? So once we've put all of these points down in here, they're not exactly connected. And here, here's all the same points in a TI-84. This book presumes that's your calculator, and I know it is actually the most common graphing calculator out there. So hopefully you got something that looks kind of like this. You may have had to change your graphing window. Notice that they're making Y run from 29.5 to 850 so that all of the points are shown. Okay. Sorry, 575 to 850, and they're letting X, the percentage, go from 29.5 to 34, because that's where all the data was. If you had it going from like 0 to 100, then your plot would have everything squeezed like right in here, and you'd have a lot of blank space, so it'd be difficult to read. So based on your data, try to get your graphing window to show things in a convenient way. Okay, as on-base percentage increases, the number of runs also increases. It's not a universal phenomenon. For example, if I look at these two data points, this team had a higher X coordinate, a higher on-base percentage, but a lower runs compared to this one back here. But overall, there is some sort of relationship that as on-base percentage increases, you expect runs to increase as well. Okay, so if you can kind of fit a line, this is not like an exact oh, 100%, you can definitely answer the question. But this kind of looks like a line fits it, and it's increasing. So we have a linear model with a positive slope. This kind of looks like a line, and it's decreasing, so it's linear with a negative slope. But we could have things that go up and then, that go up and then that go up and then come down, and that can't possibly be a line. Maybe it goes up, down, and up. That's not a line. And while this is always going up, it's like the bacterial growth one that we saw a couple examples ago, where the rate at which it's increasing is getting bigger and bigger. And these would all be nonlinear models. Okay. So we're going to have a bunch of scatter plots. Try to determine whether they represent a linear or a nonlinear model. Here's A, and this is nonlinear. You might have thought it kind of looks like this line fits it fairly well, but overall, I think it's really suggesting something like that, which isn't a straight line. Okay, this one here, does this look like a straight line fits it or not? I'd say this looks pretty linear. It kind of looks like we've got a line like that. This one here also looks linear, going down. And what about this? I'd argue this is probably not linear. It looks something like this, where here it's going down quite fast, but as the x value increases, we are kind of flattening out. And if the rate of change is itself changing, that's not linear. Remember, a linear function is where the average rate of change is always the same value, the slope. Okay. Let's do one more example in this video. So find a model for some linearly related data. Okay. Use the data from a previous example, which we'll see the data again, don't worry. Select 2 points to find an equation of the line. Graph the line on the scatter plot, obtained by the previous example. So here is all that baseball data again. Okay, select 2 points, and we're just going to use, where are they? 31.5, 690, and what was the other one? 33.1, 778. Of all the 2 points we could have picked, I guess we just picked these two. The way the problem was phrased, of course, it just said pick any 2 points, but we're just going to go with these two. Okay. So how am I going to compute the slope of the line connecting this point and this one? It's delta y over delta x, so let's make this the first point and this the second point. So we do y2 minus y1, that's 778 minus 690, over x2 minus x1, and that's 33.1, 31.5, and we get a slope of 88 over 1.6, or 55. Okay, so now I've got a line, and I know I want its slope to be 50, and I want it to go through this point right here. So how am I going to find the equation of the line? Well, I don't have an intercept, but what I do have is a point and a slope. So we'll use point-slope form. So what is the equation of this line in point-slope form? The line with slope 55 and passing through that point, 31.5, comma, 690. Well, if we use point-slope form, it's right here. We put y minus 690 is 55 times x minus 31.5. Distribute that 55. Okay, honestly, at this point, it's obviously a line in point-slope form, but if you want to convert it into slope-intercept form, you can do so. Okay, y is 55x minus 1042.5. Okay, part B. Here is the scatter plot, and here's the line we drew. It looks like a fairly good fit. I do want to point out, if you had picked, for example, these 2 data points, you would end up with this line, which would be a very bad fit. So knowing in advance what the line was going to look like, I suppose the book picked 2 points that fits pretty well. What you could also have done is hand-drawn a line that you think looks the best, and then find 2 points closest to it. So if I just hand-drew a line that I thought was the best fit, I might say, you know, this point here and this point here look like very good fits to the line, and then I would go from there. Okay, so we'll come back for a new video just to keep them individually pretty short for this example here.